Hello everyone, this is Sheng from Peking University, and today I'm very glad to present our work, KUBEDIRECT, unleashing the full power of cluster manager for serverless computing. Serverless computing, also known as function as a service or FaaS, gives us a very simple abstraction, computation at function granularity. But beneath that simple interface, the platform still has to do all the hard management work: auto-scaling, instance lifecycle, and runtime. And because of that, many FaaS systems are built on top of well-developed and feature-rich cluster managers, especially Kubernetes. It is a natural choice because Kubernetes is already good at low-level resource management, so FaaS platforms only need to implement their platform-specific policies on top and reuse Kubernetes for the heavy lifting below. And the value of Kubernetes is not just low-level orchestration. It also comes with a rich ecosystem of extensions, such as service mesh, monitoring, and storage components. That ecosystem matters a lot because it gives us important functionality out of the box. So compatibility with Kubernetes is not just a convenience. It is a major practical consideration. Kubernetes gets these advantages from a specific design philosophy. It is state-centric. Cluster state is represented as a collection of API objects, and management logic is distributed across a series of controllers, which are state machines that subscribe to the API objects through the API server and the etcd storage backend. So controllers do not call each other directly. They communicate in a uniform fashion by publishing and observing state changes. That gives Kubernetes declarative interfaces loose coupling and strong extensibility, which is exactly what enables its broad ecosystem. But that same design can become a problem for FaaS. FaaS workloads are highly bursty, and that could lead to 10,000 or more instance creations per minute in production. Meanwhile, in Kubernetes, one upscaling call expands into a chain of state transitions across multiple controllers. Every stage writes state, persists it, and notifies the next stage through the API server, and could get rate limited. So the takeaway is that burst handling is amplified by the control plane before it reaches the data plane. So given the high volume of state exchange under bursty FaaS workloads, a centralized message passing bottleneck can show up. So as a result, we find that Kubernetes can take tens of seconds just to provision a few hundred instances. And tens of seconds can be harder to afford for FaaS. This bottleneck occurs directly on the function serving critical path. However, functions are short-lived. In the Azure functions trace, the average is only around 800 milliseconds. So the control plane delay, it can easily dominate the useful execution time and inflate tail latency for users. In contrast, the data plane has been aggressively optimized, and sandbox startup can be done to just a few milliseconds. So the problem is no longer only the runtime. If we want Kubernetes to work well for FaaS, we need a much faster control plane. One approach is clean-slate redesigning the cluster manager. The state-of-the-art Dirigent is a strong example of that direction. It moves away from the loosely coupled Kubernetes architecture towards a monolithic control plane, which simplifies internal state exchange and improves performance, but the price is compatibility. It involves considerable engineering effort to cover critical functionality and has weaker support for existing ecosystem. We don't want to trade compatibility for performance. We want both. For performance, we need to bypass the centralized message passing bottleneck. And for compatibility, we want seamless integration with native controllers and out-of-the-box support for external extensions. The two goals finally lead to KubeDirect, a Kubernetes-compatible cluster manager, but scales out much faster. So how do we make this real? Our key insight is that Kubernetes-based FaaS platforms share a common narrow waist. In the middle, there is a sequential controller chain, from autoscaler to deployment and replica set controller and to the scheduler, and finally to the kubelets on the cluster nodes. But we are not going to dig into the details on how these controllers work, because our focus is solving the message passing bottleneck. And we are going to let these controllers run as is. So back to that chain, what we do know is that its upstream mainly does offline configuration, and its downstream subscribes to it and does data plane runtime setup. So this narrow waist is exactly the right scope for optimization. It dominates critical path latency, and it is also cleanly separated from the rest of the platform, which means we don't need to change how users submit functions or how external components depend on them. Then, inside the narrow waist, we observe two properties that makes API server bypassing entirely possible. So the first is sequential writes. Because controllers in the narrow waist are organized as a chain, they update the desired state in a stage-by-stage fashion. So at each stage, there is effectively a single authoritative writer. That means we do not really need the API server to resolve conflicts in a centralized manner. Instead, direct P2P communication becomes feasible. The second property is rollback tolerance. The etcd storage backend behind the API server persistently checkpoints every state update. But for half-provisioned instances through this narrow waist, they remain actually fungible and they do not require persistence. This is because it has no external side effects and remains totally invisible to the outside. So if we lose one pending instance, the platform can create another equivalent one, and the user visible meaning is unchanged. And what's more, controllers are already designed to run reconciliation loops. So if some intermediate state is lost or rolled back, they can observe it and repair it automatically. So putting these two properties together, we get the main design decision of KubeDirect. Because writes are sequential and the intermediate state is rollback tolerant, we can bypass the API server and etcd along this narrow waist and use direct P2P message passing. Well, that sounds promising, but it raises three challenges. First, without a single source of truth, how do controllers agree on the cluster state? And second challenge is that lifecycle semantics are asymmetric. While provisioning can roll back, termination cannot. And third, from an implementation perspective, we want to be minimally intrusive to controllers. We want to seamlessly integrate with them and keep their control loops largely intact. So to reason about what we are trying to solve, it is useful to compare it with chain replication. The shape looks similar because both have a chain, but the semantics are much harder in our case. In chain replication, passive backups mainly copy the primary. But in the narrow waist, each stage is a heterogeneous controller, issuing asynchronous updates, and some are even non-idempotent. That means a message is not just a replicated log entry. It can trigger new decisions and updates. So we can't just borrow the established idea of chain replication. And these slides show one anomaly why we can't do so. If we simply use fast forwarding, then consider this case. The scheduler decides to place a pod, which is a Kubernetes term of a function instance, and the kubelet instantiates it. Then they disconnect. During this disconnection, if the kubelet evicts that pod, and when the connection comes back, the scheduler simply fast forwards its old state downstream while still containing that pod, then the kubelet may recreate a pod that should already be gone, and even with a new IP address, which is undefined behavior. So the key observation here is that in case like this, the downstream side turns out to be the actual source of truth. So instead of treating upstream as authoritative, KubeDirect always feed the downstream truth backward for consistency. And that gives us the right state model, a hierarchical write-back cache. Desired state is forwarded opportunistically downstream, while the downstream truth is fed backward, upstream as cache invalidations. Each controller caches the desired state of the next stage below it, and correctness comes from keeping each adjacent pair in agreement. And this is the core shift in our design. Pairwise agreements get to replace the old centralized coordination. And we implement those agreements with two kinds of invalidation signals. Hard invalidation is used on disconnect or crash. It forcefully rolls back the state and uses a synchronous handshake to re-establish agreements. And soft invalidation is used while the connection is live. It carries incremental changes asynchronously as feedback. And this slide gives two examples. On the left, if B and C disconnect, then when they reconnect, B first resets to C state, its downstream, through hard invalidation. And then B can send its change set upstream through soft invalidation. And on the right, if B crashes, then recovery again starts by resetting against downstream state. And only after that do we re-establish the upstream agreement. So in both cases, recovery is driven by downstream truth, not by replaying possible stale upstream state intent, and that pairwise handling can naturally extend to autonomous recovery of multi-point failures in the chain. And for the next challenge, lifecycle semantics, especially of termination, is the remaining problem. Since this is the place where rollback is not acceptable, our solution is to employ a special kind of API object, the tombstones. A tombstone replicates the intent to terminate downstream. But unlike arbitrary controller updates, termination is inherently idempotent. So here we can adopt a chain replication style handling. And by lazily garbage collecting tombstones only on downstream feedbacks, we can ensure that terminated instance can never come back because the downstream can only send the feedback once the truth is established there. So in practice, this provides a fast path for downscaling as well. And finally, from an implementation standpoint, KubeDirect should fit into existing controllers with minimal disruption. Essentially, we just add an extra pair of ingress and egress modules for forward propagation and backward invalidation, and normalize them through the common object cache in standard controller architecture. So the original control loop can keep working in the usual way. The code changes are minimal, about 150 lines per controller in the narrow waist, and externally, we still support extensions like Prometheus and Istio. Our prototype also employs optimizations to minimize the amount of state exchange. For example, we only send the dynamic attributes instead of the full set in forwarding and soft invalidation. And for hard invalidation handshake, we version check the object keys to derive the change set before exchanging the values. Please refer to our papers for details. And for evaluation, we use an 80-node Cloud Lab cluster. At the cluster manager level, we compare KubeDirect against vanilla Kubernetes. And at the platform level, we compare against Knative and the state-of-the-art clean-slate system, Dirigent. In micro benchmarks, KubeDirect scales much faster across different burst sizes. Total upscaling latency is improved by 3.7 times to 16.9 times over Kubernetes. And more importantly, the latency breakdown across the controllers shows why. The message passing overhead is no longer dominating the critical path. At the end-to-end level, we evaluate with a 30-minute clip from the Azure Functions trace. KubeDirect reduces per function scheduling delay by 26.7 times against Knative variants and has performance on par with Dirigent variants. So the takeaway is that we can get most of the performance benefits of a clean slate design without giving up Kubernetes compatibility. And we also look at failure recovery overhead based on cache invalidations. We force the controller state reset to emulate crash recovery, and the result shows that recovery stays cheap and scalable across the controllers due to the batching or parallel handshakes, which confirms that our invalidation primitives are lightweight. So to conclude, KubeDirect shows that legacy cluster managers like Kubernetes can be retrofitted for FaaS without compromising compatibility. So the key ideas are direct message passing to remove centralized bottlenecks and pairwise agreements to replace centralized coordination. Our limitation is that reduced observability in the narrow waist because the direct message passing through the narrow waist is not exposed in the original API way. And another one is that our FastPass also bypasses the API server's authentication and authorization control path. So the design is only intended for clusters where the FaaS platform itself can be trusted and can protect the low-level cluster manager from the malicious loads. So thank you for listening, and I'm happy to take questions.